Hello friends, welcome to EPG Pathshala. I am going to describe one very important model in digital electronics called as arithmetic and logic unit. It is basically used in central processing unit of the computer. We all know very well that computers are very important in our day-to-day life. We are using it extensively almost every now and then. Computer basically has got three important blocks. One is I/O, second one is memory, and third one is CPU. CPU stands for Central Processing Unit. It's basically the heart of the computer, and it consists of one of the most important blocks as the arithmetic logic unit. In short, it is called ALU. ALU performs arithmetic and the logic functions required for computations in a computer. Let us concentrate only on the arithmetic part of the arithmetic logic unit. Arithmetic logic unit basically consists of adder, subtractor, multiplier, divider, etc. Other functions are also there, but addition and subtraction are very important. We know how we do decimal addition. Computer does not do decimal addition. It converts the numbers which you want to add into binary and then it adds them. So, it is very important to know how the binary addition and the subtraction is done. Once it is clear, the other operations can easily be performed by using addition and the subtraction. For example, multiplication is multiple additions and division is multiple subtractions. Logic operations are also there. Logic operations are performed by this arithmetic logic unit. Basically, these operations are AND, OR, etc. Let's try with the basic adder circuit. Learning objectives. Let us first see what we are going to learn in this particular module. To learn basic binary addition and binary subtraction, to explore the types of the adders and the subtractors, construct them using various logic gates. Let us see the introduction to the binary operations. The most basic operation is addition of two binary digits. The simple addition consists of four possible elementary operations. These are: first is 0, if it is added with 0, the result gives 0. But if 0 is added with 1, the result is 1. And if 1 is added with 0, the result is 1. If you go for addition of 1 and 1, the result is 1, 0. 1 in this is carry and 0 is addition or sum, you can call it. Let us talk about the half adder. We will see why it is called half adder later on. A combinational circuit that performs the addition of the two bits is called as the half adder. The truth table for the half adder is very simple. It is as below. Let us assume that there are two inputs x and y. Result is sum and carry. If x and y are 0, 0, sum is 0, carry is 0. And as I said, if you want to add 0 and 1, commutatively also the result is 1. But if you want to add two bits which are ones, then the sum is 0 and the carry is 1. This is basically the truth table for the half adder. Let us see the K-map for some of the half adder. You have to fill up this particular table. If you look at the truth table, you will find that if x dash and y dash is 0, 0, nothing is to be filled up in the table. Leave it blank. If x is 1 and y dash is 0, then the sum is 1. That is why in that particular block or square 1 is written and it is designated as x y dash. The next one in the truth table you will find at the place where it is x dash y. Corresponding block is filled with 1. If you write the expression for this, sum, then you get that as x dash y plus x y dash. Effectively, it is the exclusive OR operation of the two variables x and y. K-map for the carry of the half adder is more or less same as that of the sum. K-map is drawn in the same manner, x dash x, y dash y, and we have to fill up this particular K-map. So, if you look at the truth table, you will find that you get carry only when x is 1 and y is 1. The rest of the blocks are not to be filled up, so they are left blank. So, carry corresponds to the operation which is AND of the two variables x and y. So, if you write the expression, it gives you carry is equal to x and y. Logic diagram for the half adder then can be easily drawn by using these two expressions. The two gates which are used are OR gate and the AND gate. The output of the exclusive OR gate is sum and the output of the AND gate is carry. The two inputs are applied to both these gates. This particular circuit is called as the half adder. It is called so because it does not accept the carry as one of the inputs. Normally, when the addition is carried out, sometimes you need to add 3 bits. So, if you can add 3 bits by an adder, then it can be called as the full adder. Truth table for the full adder is as shown below. It has got 3 inputs and 2 outputs. X and y are the normal 2 inputs, and Z input basically is the carry in input, and the other 2 outputs in the truth table are carry and the sum. Carry here is the carry output that is generated, and sum is obviously the addition of the 2, the 3 inputs now, because it is a full adder. By using those expressions which are already considered for basic binary rules of the addition, you can explain how this truth table is obtained for the full adder. If you look at this truth table, you will find that there are ones in carry at 4 positions and there are ones in sum at 4 positions. Likewise, we can obtain the expression for the sum and the carry of the full adder. K-map for the sum of the full adder. As there are 3 variables, K-map here is different. You have to incorporate the 3 variables. On the horizontal axis, 2 variables are incorporated. On the vertical axis, a single variable is incorporated. Let us take x on the vertical axis, y and z on the horizontal axis. So, for filling this, these are equivalent to 0, 0, 0, 1, 1, 1 and 1, 0, not 0, 0, 1, 0, 0, 1 and 1, 1. The order has to be like that only, because then only you can use it for K-map. So, if you look at the truth table for the full adder, you will find 1 in a block corresponding to x dash, y dash and z. So, it is filled up with 1. The next block where you find 1 is x dash by z dash. Correspondingly, it is filled with 1. If you just go ahead, you will find 1 at the place where it is x, y dash and z dash. So, 1 is filled up with there. The last one remaining is filled up at the place where x is equal to 1, y is equal to 1 and z is equal to 1. So, if you look at this K-map, you will find that there are 4 places where there are 1s. The expression for the sum can be obtained by using these 4 blocks where there is 1. So, expression is sum is equal to x y dash z dash or x dash y z dash or x y z or x dash y dash z dash. Actually, if this expression is implemented by using logic gates, it will require one 4 input OR gate and 4 3 input AND gates. So, it will be a very lengthy circuit or complicated circuit. Instead, this expression can be simplified as the exclusive OR expression where the 3 parameters x, y, z are involved. Easily it can be worked out. It can be seen from the expression for the sum is equal to z exclusive OR x exclusive OR y. By using the formula for exclusive or if you evaluate this, you will find that you get the expression for the sum that will be obtained by using the K map. Therefore, one can say that sum of the 3 parameters in a full adder can be obtained by using 2 exclusive OR gates. Like we have worked out the sum of some expression, we have to work out for the carry expression. Again in this carry, there are 4 places where there is 1. Let us fill up the K map one by one. The first place where 1 appears is filled up at the place where it is x dash y z. Let us go for the next line of the truth table. The next line of the truth table fills up the place which is corresponding to x y dash z. Obviously, inside the box 1 is written. Again observe the truth table for the full adder. The third place can be filled up by the place corresponding to x, y, z. If you observe the last place in the truth table for the carry, you will find that it corresponds to x, y, z dash, and therefore 1 is filled up at the place where there is 1. By having pairs from this K map, one can write the expression for the carry. The expression for the carry is x exclusive OR y multiplied by z plus x y, and expression for sum is x exclusive OR y exclusive OR z. This full adder can be obtained by using 2 half adders. The first half adder uses xy and the second half adder uses the exclusive OR corresponding to x, y and z. So, first the addition of the 2 bits is carried out and then it is added to the third bit. Similarly, for obtaining the carry, the 2 AND gates are used and then finally OR gate is used. The circuit is giving the perfect expression for the full adder. So, friends, if you want to have a multi-bit addition, now you can see that number of full adders will be required, and these full adders are connected in cascade manner. There are 4 full adders. Now you want to add 2 4-bit numbers. Of course, the decimal numbers are converted into corresponding binary bits, and those binary bits are added by this full adder. There is MSB adder and there is a LSB adder. Actually, you start with LSB adder. LSB will be applied to least significant bits, and the carry to it mostly will be absent because this is the first bit addition. The result of this addition will give you sum and the carry. Sum will be available at the output and the carry will be given to the next adder. The next adder is going to be a full adder. It will have 3 inputs. It will have next significant bit to LSB. So, it will be adding A1 and B1, and as a result again it will give you sum and the carry. Sum can be taken out and the carry is given to the next adder. The process is then repeated for the next bits which are A2 and B2, and then finally you will get the sum and carry, and the carry that is generated will be given to the next adder. Sum obviously will be taken out and the last adder will give you the 4th bit, which is the addition of the most significant bits, and it will generate the carry of the overall addition. So, if you want to add 2 decimal numbers, first of all obtain their binary equivalents, then apply them as the inputs to this 4-bit binary adder. The result obtained is the addition of the 2 numbers S0, S1, S2 and S3, and obviously A0, A1, A2, A3 is one number, B0, B1, B2, B3 is the another number. C4 can be used if it is required for further addition. Let us take the binary addition. Let us assume that the two numbers which you want to add are 11 and 3. Obviously, these are the decimal numbers. You know that their addition is 14. Let us work out this addition by this binary adder. 11 is converted to binary number as 1011 and 3 is converted to binary number as 0011. So, if you add these two, then the first number is adjunct, second number is addend. If you add 1 which is LSB, you get the sum as 0. Obviously, this generates a carry and that is applied as the carry input to the next adder. So, next adder will have 3 ones for addition. So, as a result, it will give the sum as 1 and also the carry as 1. For the next addition, the 2 bits are 0, but the carry is 1, so the addition is 1. This does not generate the carry, so carry is 0, and the last bits are to be added. The addition gives 1. So, if you find out the sum, it is 1 1 1 1 0, and if you convert that into a decimal number, it will correspond to 14. 11 plus 3 is 14, we know very well, but the same thing is obtained by using this particular full adder. Multi-bit half subtractor is shown in the diagram. It again has got the two 4-bit numbers to be subtracted. B0, B1, B2, B3 is the number from which A0, A1, A2, A3 is subtracted. So, 4 full adders are used. The circuit diagram is basically same as that of the binary adder. Only thing is the ones complement is first obtained for the subtrahend B0, B1, B2, B3. That is done by exclusive OR gate, and then it is added to the input of one of the full adders. This is done bitwise. For example, if you take full adder first, which generates the subtraction bit S0, then A0 and B0 is added. So, the exclusive OR gate that is used for B0 generates its ones complement, and then it is adding 1 to it, and then finally full adder gives the subtraction of the two bits A0 and B0. Similarly, the process is carried out for the other bits and the full subtraction is obtained. Suppose the second number is bigger than the first number, then overflow is generated. This is indicated by V, which is again obtained by using one exclusive OR gate, to which C3 and C4 carries generated by the full adders are added. So, even though the full adders are used, the circuit works as the binary subtractor. This slide indicates the concept of full subtraction. Two NOT gates are used and two half adders are used. Obviously, one OR gate is required. So, two half adders and two NOT gates constitute two half subtractors, and if they are combined together, you get the full subtraction. The D bit here is the subtraction and B0 bit is the borrow. If required, this borrow can be carried out for the further subtraction. There is one important adder circuit that needs to be discussed. This adder is called as the carry look ahead generator. Let us say its importance. If the parallel adder is used, it accepts the data to be added at the same instant, but the carries are not generated at the same instant. It takes some time for the carry to propagate from LSB to MSB, because only if the LSB adder generates the data can go to the next full adder. So, this concept is called as the carry propagation. So, it takes time for the carry to go from LSB to MSB. As a result, the total propagation time is equal to the propagation delay of a gate multiplied by the number of gates used in the circuit. And if you see this parallel adder, there are so many gates used. So, as a result, the addition is very slow. If you come to the MSBs, the inputs A3 and B3 are available as soon as the input signals are applied to the adder, but the carry is not available because it takes some time to settle to its final value, because C3 does not settle to its final value until C2 is available. C2 has to wait for C1, and similarly C1 has to wait for C0. Thus, only after the carry propagates from LSB to MSB and ripples through all the stages till the last output is generated, the final addition is not obtained, and the correct value will be obtained only after some time. So, the addition is delayed. This kind of concept is called as the carry propagation concept. So, let us see how we can reduce this particular time of addition. The carry propagation time is obviously the limiting factor if you want to have a fast adder. The adder will always have some values at its output terminals. The correct value will be provided only when the signal propagates till the last point. So, the time consumed during the addition is very critical. This time has to be reduced by some means. The means that is used for reducing this time is called as a carry look ahead principle. As the name suggests, you are going to look for the carry in advance. So, this will reduce the speed of addition and the addition will be faster. Let us see the solutions. One solution for reducing the carry propagation delay time is to use the faster gates which have got very less delays. Another solution is to increase the complexity of the adder circuit in such a way that the carry delay time is reduced. Of these two techniques, the second one is better. Obviously, there are several other techniques also for reducing this propagation delay time in the parallel adder, but the carry look ahead principle has turned out to be the best one, and it is most widely used principle for getting the fast adders. To understand this principle, we have to talk about a technique. The technique used with the help of the full adder is obtained by using the exclusive OR and the OR gates. With slight modification, if we define two new binary variables Gi and Pi, carry look ahead principle is used. Gi is the carry generator, Pi is the carry propagator. Let us use the same expression for the half adder and obtain Pi and Gi. Pi is equal to Ai exclusive OR Bi and Gi is equal to Ai Bi. The output sum and the carry can respectively be expressed as Si is equal to Pi exclusive OR Ci and Ci plus 1 is equal to Gi plus Pi Ci. Here I stands for a particular bit. For example, if you are trying to talk about the LSB, I will correspond to 0, whereas if you talk about MSB, then I will correspond to 3. These expressions are used to generate the carry propagator bit and the carry generator bits. Pi and Gi bits are very useful for increasing the speed of the addition. Gi is the carry generate bit and it produces a carry of 1 when both Ai and Bi are 1. Regardless of the input carry Ci, Pi is called as the carry propagate because it determines whether a carry into the stage I will propagate into stage I plus 1, and the carry is available in advance. If you use these expressions for carries, we can obtain them in details. C0 is the input carry, most of the times it will be 0. C1 is equal to G0 plus P0 C0. C2 is equal to G1 plus P1 C1. If you substitute C1 from the earlier expression, finally you will get C2 as G1 plus P1 G0 plus P1 P0 C0. By using the same expression, the final C3 is obtained as G2 plus P2 G1 plus P2 P1 G0 plus P2 P1 P0 C0. These expressions are very important to obtain the final carry look ahead adder circuit. Let us see where we will get our addition. Addition will be available at the 4 bits S0, S1, S2, S3, and the expressions for them are basically exclusive OR expressions. So, by using 4 exclusive OR gates, we can obtain the 4 outputs which are S0, S1, S2 and S3, and they basically use these carry propagate and carry generate bits. The carry look ahead generator then generates the 4 sum bits S0, S1, S2 and S3. If we look for the circuit diagram or block diagram of carries generated in advance, it is as shown below. So, if you look at this particular block diagram, you will find that it accepts the carry propagated and the carry generated bits which were obtained by using the expressions. These bits are C0, G0, P0, P1, G1, P2 and G2. The expressions are implemented by using 6 AND gates and 3 OR gates. Out of these, the 2 input AND gates are 3 in number, 3 input AND gates are 2 in number, 4 input AND gate is 1 in number, and OR gates carry 4 inputs, 3 inputs and 2 inputs. So, this particular diagram is nowadays available as an integrated circuit in the market. Use that as a carry look ahead generator and obtain the adder circuit. The adder circuit is as shown. This complete circuit shows the carry look ahead adder circuit. Inside it, you have one IC that works as the carry look ahead generator, and it has got 4 half adders. These half adders, they generate the carry propagate and carry generated. These are the inputs to the carry look ahead generator, and the same inputs are applied to the 4 exclusive OR gates at the output. The carries which are looked ahead are applied as the inputs to these 4 exclusive OR gates. As a result, you get the sum S0, S1, S2 and S3. As the carry is looked ahead or in advance, this is going to be a very faster adder, and this has to be a faster adder circuit because the other circuits obtained into the arithmetic logic unit use this as a basic adder circuit. For example, if you want to obtain the multiplier will have adder, and if adder is slow, multiplication will be slow, or you may get a wrong result if a slower adder is used. Therefore, this finds many applications in the actual arithmetic circuits. The circuits which were described find lot of applications in arithmetic units. For example, multiplication is multiple addition, division is multiple subtraction, and ALU basically carries these 4 operations: addition, subtraction, multiplication and division. Therefore, ALU is obtained by combining all these basic arithmetic operations. As I said, ALU is the most important block of CPU. CPU is the heart of the computer. Computer works only if the CPU is in order, and CPU works only if ALU is in order. Therefore, these arithmetic circuits carry a lot of importance. So friends, in this module we learned one of the most important blocks of the computer, that is arithmetic logic unit. We started with the basic simple circuit called as the half adder. Half adder is the one which accepts 2 inputs and it gives the addition as well as the carry. But this is half because it does not accept the carry that is generated because of the previous addition. So you need a adder called as the full adder. This adder will accept the 2 bits which you want to add and the carry that is generated because of the previous additions. This basically is obtained by using exclusive OR gate and the AND gate. The 2 are combined together, meaning 2 half adders are combined to obtain the full adder, and 1 additional OR gate is required. After the full adder is available, it is possible to obtain the subtraction also, which we can call as the full subtraction. In full subtraction case, it will accept the borrow as one of the inputs. Subtraction is basically the addition. Only thing is it is 2's complement addition. So if you want to carry out the subtraction, first of all you have to obtain the 1's complement, add 1 to it, it will give you 2's complement, and then add it to the number that you from which you want to subtract. So as a result, you will get the subtraction. So multi-bit adder and multi-bit subtractor can be obtained by using full subtractor. Only thing, when the circuit is to be used for subtractor, NAND gates are required, or you can use exclusive OR gates to obtain the 1's complement and then add 1 to get a 2's complement. If these circuits are used, one can obtain multiplication as well as division, because multiplication is multi-bit addition or multiple additions and division is multiple subtraction. So arithmetic unit of the central processing unit consists of these 4 operations, which are addition, subtraction, multiplication and division. It has got a logic unit also. This logic unit does the basic logic operations like AND, OR, etc. And if these 2 are combined together, meaning arithmetic and the logic operations, you get a block called as the arithmetic logic unit. This is the most important block in CPU, and CPU is heart of the computer. So if you got ALU working fine, CPU works fine, computer works fine. Thank you friends.